Imagine NASA offers you 100 crore rupees for a very specific, very strange mission. Not to land on Mars and not to visit the moon. Your only job is to touch a black hole. There is exactly one rule. You touch it for exactly 1 nanosecond. You pull your hand back and you come home to collect your money. To understand how short that duration is, light itself only manages to travel about 30 centimeters in a single nanosecond. With an exposure time that short, a billionth of a second feels like a safe margin for error. It just seems like an easy payday. We will even assume the environment is perfectly controlled. Your spaceship is hovering safely, no deadly radiation flying around, and the black hole is calm. The hatch opens, you reach out, your fingers slowly approaching the total darkness, ready to make contact for just 1 billionth of a second. At this scale, human intuition regarding time and safety collapses. The edge of a black hole operates under a set of rules that our biology is not equipped to handle. Let's freeze the experiment right at the moment of contact. If you touch the edge, even for a nanosecond, you are already dead. Gravity is a constant presence. The Earth pulls on you, as does the moon, and even the chair you're sitting in right now. These forces are uniform enough that they don't cause us harm. Survival depends on the uniformity of that pull. Near a black hole, tidal force creates a lethal gradient. Your fingertips are pulled with much more intensity than your shoulder. This tiny difference translates to a mountain-sized disparity in force. Physicists call this spaghettification, the violent dragging of your body apart. If we unpause the clock, you are stretched and ripped apart long before that single nanosecond ever expires. Small black holes pack their mass into incredibly tight, sharp curves, creating an extreme gravity gradient that makes them instantly fatal shredders. Since test 1 ended in complete destruction, let's reset the scenario and change our primary variable. Instead of a small black hole, we use a supermassive black hole. These objects contain the mass of millions or even billions of stars, all packed into a single point. This leads to a deeply counterintuitive quirk of physics. As a black hole grows larger and more massive, the tidal forces at its outer edge actually get weaker. Because the enormous size creates a much gentler physical curve, the gravitational pull on your outstretched fingers and your distant shoulder is now nearly identical. Under our 1 nanosecond rule, the lack of an extreme gravity gradient suggests your body could maintain its integrity. You might actually survive the touch. In the realm of extreme astrophysics, increasing the mass creates a surprisingly gentler physical threshold at the event horizon. We start test 2. You reach out toward the supermassive black hole, and you make physical contact for exactly 1 nanosecond. The clock ticks down. 1 single nanosecond passes, and your physical structure remains completely intact. But when you try to pull your hand back to claim your reward, you realize you can't move. Surviving the stretching force of gravity is a totally separate issue from escaping the total strength of the gravitational well. By making contact, your hand has crossed the event horizon. At this specific boundary, the required speed to pull away exceeds the speed of light, meaning no amount of thruster power can recover you. There are no rescue missions possible. If the rest of the crew wants to survive, they have to fly away without you. You have successfully completed the 100 crore NASA mission and survived the touch, only to become the most expensive one-way science experiment in history. The 1 nanosecond limit was always irrelevant. Touching an event horizon represents a permanent change in physical state, regardless of the clock. Which leaves one final question. What actually happens when you inevitably fall all the way inside?